And just a second, and we are live.
All right. Good morning, everyone. So I wanted to emphasize an important thing before we got into the lectures today, or our discussion really, because I'd rather it be more of a discussion. We're going through Khan Academy, at least we're using it for a pattern for the way we're studying linear algebra. I think Saul Khan does a great job teaching it. He lays out the concepts really well. And this is our third meeting, and we're going over linear dependence and independence in vectors and spaces. And each of these is a section. I'm going to go to this section. I hope that you are watching the videos. So again, here we are. We did this, a portion of our ongoing notebook. And we'll have a notebook for vectors and spaces most likely, and then we'll start a new notebook for the new section. But the first session we had together was doing NumPy and Matplotlib in a way that followed this first section. And then the next part of the notebook followed this lecture, which was foundational to this one. So what I'm hoping you guys are doing is watching these before we meet. And it's okay to watch ahead, and it's okay to not understand everything. We're using NumPy and Matplotlib, and we'll probably use other Python modules and tools to help us understand these principles better. So, I mean, I don't want you to be afraid to show up if you didn't watch the videos first, but you'll do so much better if you watch the videos, think about them, and maybe watch them again and think about them some more. I want to share something with y'all that occurred to me recently as I was helping some of your friends around the world. It occurred to me as I looked back and I thought, now, why do we struggle with new stuff? Well, when we were toddlers, or when we watched toddlers, they're learning to walk and they're learning to talk. I guess even before a toddler, you're learning to walk. And, you know, they don't stop to think about, this is hard. Wow, why is this so hard? No, we begin to think about that when we get older because we're relating it to other things, but we don't usually remember learning to walk and talk. But if you watch a baby learning to walk, or you watch a toddler learning to talk, you know, it doesn't go really good at first. And I just want y'all to remember, when we start in a new area, we're kind of like babies all over. In that new area, we're learning to walk and talk. And again, the walking's not perfect in the beginning, the talking's not perfect in the beginning. But how do we learn to talk? We're exposed to the new language. So Saul talks about this stuff just about better than anyone I've seen. And then learning to walk in it is the code, you know, or even the talk. But it's a good analogy. So guys, be gentle with yourself. Just keep at it. Just keep watching the lectures again, thinking about them, running the code, thinking about what we're doing in the code. And I want to promise you something. When we're watching these math lectures, even from someone who's as clear as Saul, we can get confused, like, why are they going at it this way? We kind of want to rush ahead, but it's kind of like this fast, wide river we're trying to cross. And there's these stepping stones just under the water. And if you try to jump ahead too fast, you miss some important foundations and you get swept down the river and you find you got to swim out and start over again. So have a spirit of, okay, he's making a point here. All this stuff took thousands of years to develop. Let me take my time with it too and trust my original teachers. And then someday, trust me, your thoughts can go higher, just like the people who brought us greater math in the centuries that followed the guys that originally came up with stuff before then. So it's a spirit of trusting it. Now, what often happens too is the principles that are being laid out are so insanely simple conceptually. It's hard to imagine that's the point they're making. But trust me, a lot of times with math and engineering related to math and to modeling, that's what's going on. So as we extend our notebook, the first thing I want to do, boy, let me see if I can move my, oh, good. I can move my control bar. That's a good feature. Okay. So I trust you can still see my screen fine, correct? Where we're here on Khan Academy?
Yes,
Now,
absolutely.
excellent. And Ayodeji, when I ask these questions, since you're on camera, give me a head nod. That'll help me because I can see you. I can't see everyone. Thank you, brother. All right. So I'm going to go. First, I'm going to just copy this link address. And don't hesitate to ask me to make my screen bigger. Now, you guys had asked to have me code while we talk, and I do think that's better because you get to see how the work progresses when it's laid out. But it will, I think the teaching will be better that way, but it doesn't mean it'll go faster. So let me look back here. I already lost. Oh, it's there. Okay, so we're talking about linear dependence and independence today. So let's just type that out as a placeholder. And think about that as I'm typing, start to ponder it. I think you probably got a good feel for it if you followed the last lecture. I hope if you had questions, you will ask them. And let's go ahead and learn how to make these nice links to things. So we get to put that link that I copied right there. This will be a placeholder so you can go back and watch the lectures when you're not clear on something you see in the code. And that first lecture was called Introduction to Linear Independence. Very important principle, especially for who? Data scientists, machine learning engineers, artificial intelligence scientists, any data specialist, really. And these, I really, I have watched all the linear algebra lectures before, but guys, even at my level, it was so good to watch them again. I was glad to do it. And then,
Sorry, Papa, can you please expand, maybe zoom out a bit?
yes, I was going to ask if it was big enough yet. All right, there we'll get that level there. And then on our notebook, that one was probably the more important one, right? How about that? Is that pretty good?
Just a little more.
Oh, yes.
Okay, great.
Wow, that, I don't think I went out anymore though. There we go.
Great.
So then the next one, good. The next one is more on linear independence. So we'll go to that. And I'll need the link for that one. So copy link address. And by the way, guys, when you're making your own notebooks, like you're making your own notes because you're experimenting in code with something you've studied in math, this is a great practice. I didn't have this when I was your age. For a lot of my young man years, we didn't really even have the internet yet. So it wasn't an instant transition, like all of a sudden, oh, we're doing everything on the internet. But sure is nice now. You can get your hands on things so quickly. span and linear independence example. Okay, great. So that's just so that we can reference these really quickly. Oh, we might as, here we'll go to do this too. I'll go ahead and do a second layer one. And this is just linear dependence and independence is what we'll name the section link. So that'll take us right to this section, copy link address. Just remember square, then round, and you can always do this. My short-term linear dependence and independence. And when y'all are watching me just type, I hope you're thinking deeply about, just preparing your brain. Well, what does that mean? Because that's the way we want to be. I think I'll make that one smaller. There we go. So those are our links to those videos, and that's what we want to cover today. Well, you've probably already heard this before, but maybe it'd be good if I type some extra notes. Let's call this an overview. When we say linear dependence, this means that there's no collinearity between two vectors. Now, we often use the language features in machine learning. So let's say, what do we do? We can use a parenthesis to say that is features. Okay, that's what we're really talking about. And when we say there's linear dependence, what would it be? And y'all feel free to come off mute and just talk with me. But linear dependence means that collinearity is present between two or more vectors, i.e. features. Well, that's interesting. Now, depending on where you're at in your data science education, this may not mean as much. But what you have hopefully seen is our lecture on span. And here we have these two lectures, we have these two vectors, V1 and V2. And we could see right away that, well, these two vectors are pointing in the same direction. They just each have different magnitude. And when we looked at the span, we could in fact see that even though they were two-dimensional, what was going on? When we looked at the span, and again, we're not looking at the entire span, right? We were just looking at a subset of the whole span. We were only using integers, not all real numbers. For example, I'm going from -5 to -4 because I'm stepping by one. But if they were real numbers, you could step by some really, really small amount, and the computer couldn't have completed it all. So span is a conceptual thing we can't even perfectly represent in matplotlib, but basically it would just color the span, and it'll be more clear when we look at our other example. But here we can see that even though we have two dimensions, we couldn't fill up all the real numbers in two-dimensional space. In fact, we ended up in a one-dimensional space. Well, That's because this vector is not giving us any new information. As I went through all the possible linear, well, not all, but all the integer possible ranges between -5 and 5, and don't let me confuse you, what this means is we're going right before 5. In fact, something I did in my LinkedIn post, if y'all saw it, we'll call this finite span. And then what we could have done is just call this finite span. This way we can change one number. In fact, that wasn't really the best programming style when I did this with just numbers. But again, we're not trying to program perfect as much as understand what we're doing perfectly. And so this way I can always just have one number to change when I'm looking at these finite spans. So now when this is going to look roughly the same. But now up here in our example, we look at these two vectors and, let's also, a little trick. What I'm doing here is Control-Shift-L. Now it highlighted all the spans. And what I have is a multiple cursor. And so now when I type things, it's doing it in all 5 of those places. But here, these two vectors are linearly independent. And this one gives unique information to this one. And we can see as we start this finite span of 5 in both dimensions, whoa, we can tell if we get bigger and bigger that this is going to keep getting bigger and bigger itself. Hang on, it's just loading stuff. So you can see it's just filling out more space, and I could keep making that bigger and bigger. I could go into the NumPy A range and cause this to, we could step at 0.1, and it would take longer. That was just taking long because it was loading for the first time. But if we went 0.1 or 0.01, soon enough, the thickness of these arrows would cause us to completely just fill in the gaps here and everything. But this is just to show that we've already kind of looked at how we can check for linear independence, which is like this, these two-dimensional vectors. We can find values for C1 and C2 that would put our arrow, the tip of our arrow, anywhere in this space, this two-dimensional space. Whereas when we looked for several different values of C1 and C2 for these two vectors, when we saw that it wasn't giving us enough information to fill out the entire space, it was just on a line. So that implies if it's a line, it's one-dimensional, these are dependent on one another. And of course, we can see it directly. Well, why belabor this when it's so obvious? Because when we get into n-dimensional space, and I mean way beyond 3-dimensional space, now we got to think a little differently. If I have more than 3 dimensions, I can't visualize that anymore. I can't use this trick of just plotting, a finite span to get a feel for what the infinite span would be. So now, what do we need to do? We'll practice in 2 and 3 dimensions, but if we go beyond that, we can't really easily rely on these visual tools anymore, but we can still use them as a crutch, sorry for scrolling so much, to help us understand the deeper multidimensional principles. So let's get at it. Now we want a textbook, excuse me. We'll leave that in case we need it, and we'll do a code block. Okay, so, and please guys, sometimes it gets lonely lecturing here, so do come off mute and ask questions and stuff, not just to keep me from talking all by myself here, but more so to just make sure you're getting your questions answered. Okay, now I'm going to go ahead and keep them like this. Now, in case you didn't watch the lecture, Saul was talking about how to do this mathematically. So he was plotting things and he was looking at them in 1D and 2D and even 3D, but he was just doing that to illustrate, and we will try to do some of that, but what he was trying to emphasize is how to use the math, how to use mathematical steps to look for linear independence and linear dependence. So here is our case for linear dependence, and that'll be nice. We can go on ahead and just type that. And then here would be our case for linear independence. And we'll have some code for that. We'll go grab those two independent vectors we worked with before to make things easy. And I'm just, when you see me doing that, I'm just using my keyboard buffer. You can do Control X and then Control V. I'm using the old man's version, which is Control Shift Delete and then Control Shift Insert or Control Insert. I do it by muscle memory because I've been doing it for over 2 decades. So we can see pretty much right away. Let's do a print statement. Go ahead and do it right here. V1, V2. And that's really nice because it's laid out. But what can we see here right away? By the way, in case you weren't aware, you can do operations between rows. You can treat them like you're adding and subtracting them from one another. And right away, if I say, let's print V1 again, but let's print 2 times V2. Now they're exactly the same. And obviously, if they're exactly the same, they're dependent on one another. But we wanted to be able to see that here. But if you have 100 dimensions, you don't want to do it that way. You want to say something like this. In fact, let's be more, let's inform ourselves. This is easy to see by inspection. But what if we have many, many dimensions? We need a mathematical way, a code way, a programmatic way. And this is why programming is so popular, because we can automate this, a programmatic way to check for, oops. That's what we're saying here. So yes, we can see this by inspection, but let's find a way to just check it by code. If V1, okay. Now, this begs the question, well, how am I going to know that I needed to multiply by 2? Because we haven't gotten to those points in the lecture yet. But what we could do is turn each of them into a unit vector. And we saw how to do that before. So let's call it, let's do some other operations before we get into this one. Let's call it U, short for unit, V1. And what is that going to be equal to? We're in NumPy here. You couldn't do this in pure Python, but let's do NP for NumPy dot, and then remember linalg dot norm of V1. So we're going to turn both of these into unit vectors. And then let's be constructively lazy here. Change all these to 2 now. And then well, let's just look at those first so we can comment out that one. That was a control slash, by the way. And we'll print U V1 and print, oh, I'll fix that, U V2. And we expect them, yes, to be exactly the same. But again, we might be looking at so many dimensions that go off the screen over here. So we want to be able to check that programmatically. So control slash again, if U V1 is equal to U, keep doing that, V2, print the vectors are dependent. And then we'll go ahead and I want LF here. The vectors are independent. So we can run this again. Uh-oh. So I need to do this different. So I want to compare in NumPy, because I'm drawing a blank right now. How did I do that in the past? NumPy check 2 arrays equal. And it's just array equal. And so let's go look at it together. Array A1, A2, put them in and returns a Boolean true if the arrays are equal. So I'm going to grab that and do control insert is what I did. Or you could have done control C. Go back to our notebook. And I will paste this in here. So since it's returning a Boolean, I'm just looking for a true or false here. And it's, oh, I need an else here, don't I? It's either or, so I don't need to do the operation twice. And the vectors are dependent. Well, let's be constructively lazy. Down here, we will just, it'll be great because I should be careful here. Yeah, we'll copy this block now. That's what we want to do because we're calling these V1 and V2 also. Now we have this standardized routine for any V1 and V2. And so since we ran this operation like this, and we looked at it like that, now we could see that by inspection, but we won't do this second block. So we're going ahead and print V1 and V2 again, just to visualize them in the nice NumPy format, because isn't it interesting? Even the programmers of NumPy thought visualization, how we print these out, is important. And you'll see that the way they very nicely lay out matrices too, when we get to those, is very helpful. Okay, so I'm going to copy all this and we'll put it in a new code block here. So we just ran that, so that's still in our memory buffer for this. And the vectors are independent. And you can see after we made them unit vectors, if they were going to be dependent, they should have been the same values each. But we can see, what does this mean? It means we're getting more information. Now forgive my scrolling. I'll try not to do it too much. Here we had two vectors, but we didn't get 2 dimensions worth of information. Here we had two-dimensional vectors, and we got enough information to fill the entire 2D span. But here, just a 1D span. And now you should be both thrilled and underwhelmed, both. If I've done my job, and if you've done your job, and you've looked at those lectures, and you've been through this notebook, and you played around with the stuff before, you're realizing, wow, this is great. I now know how, when it's more dimensions in some feature or some vector than I can see on, one screen's worth, that I can find at least this way linear independence and dependence. Now, let me burst your bubble a little bit though. Well, yeah, we could turn them all into unit vectors, but now we would have to say, are all of these equal? And it could be that, just to say they're equal, well, is there some degree of collinearity? Because as you've seen, maybe in other lectures I've given or not, well, they can be partially dependent. And we'll get into that. But again, this is one stepping stone. This is one way to check that. Now, Saul did some fancy things, though, that were really good, I thought. Let's see, fill in any other. Yeah, this is good. Okay, just to check. Oh, Preman, I'm just now seeing your question. Where can I see what is going on behind? Oh, let's do that. It's up here actually, in vectors and spaces. I showed y'all right here. We're doing the Euclidean norm, meaning we're finding the hypotenuse. If you're just talking a triangle, here was a 3-4 triangle, and we wanted to know the length of the hypotenuse, and it was 5. And so that is the magnitude of the vectors 3 and 4 added together. And so I was showing y'all here V1 and V2, 1, 2, just like the vector we've been playing with. If we look at that, the entire vector is 3, 4. But to get, when we add them together, that is, because we take, let me slow down a little bit, Praman. This is, I hat is the unit vector in the x direction. J hat is the unit direction in the y direction. And if we had a k hat, and I'll go ahead and double click this so you can see the LaTeX math too. if we had a z direction, it would be k hat, but we're just working in 2 dimensions. Keep it simple to understand the general operations. And we say that the magnitude, the L2 norm is another way to say the magnitude of V3 is the magnitude of V1 plus V2. So we add the I hat components, the components of those vectors in the x direction, and the component of those vectors in the y direction. But it's the same as just having this 3, 4. As you can see, once I square them, I've got 9 plus 16, which is the square root of 25, which is 5. Now, how do we get the unit vector? We go back and we divide 3 by 5. So that would be 0.6, and that would be 0.8. But we were making them unit vectors of these two. Well, the unit vector of this, let's see if we can do that in our head real quick. That's 1 plus 4, it's 5, the square root of 5. So it'd be 1 divided by the square root of 5, and 2 divided by the square root of 5. Same thing here. We've got 4 plus 4, square root of 8. So it'd be 2 over the square root of 8 and 2 over the square root of 8, which, if you'll trust me, is the same as these numbers we got. So we started with 2, 2 in this case. 2 divided by the square root of 8 equals that, and 1 divided by the square root of 5 equals that, and 2 divided by the square root of 5 equals that. So I went through that kind of fast, but if you go back through this workbook and do it above, you'll see all of that. Looks like I went one too many here. Let's do that, and that way this outline over here will make more sense when you look at it later. There we go. By the way, do write good notes and headings for yourself. That way, as your notebooks get a little on the big side, but still contain related information, it's very easy to navigate them. So, Praman, let me know in the chat or come off mute. Let me know if that did enough for now to answer your question. And by the way, I love those kind of questions. Again, in short, it's just finding the L2 norm. The reason I'm calling it norm, it doesn't make sense to call it the hypotenuse unless it's in 2 dimensions. Okay, great. And then, but we call it, when we're going in multiple dimensions, way beyond 3, it is the L2 norm, meaning we're doing the Euclidean norm. Now you might ask, well, what's the L1 norm? I'm assuming there is one. You're right. It's what's called the taxi cab norm. It's like a taxi cab driver driving through New York City, and he's adding up his distance. It's just straight line distance, but you're not worried about which direction you were going. You're just worried about miles traveled. Okay, good. Now, Saul did some other things though, and we haven't really done it the way Saul did it yet. I think it'd be good to do that, but would it be practical to do that programmatically is what I'm wondering. And so you go, do you remember if Guy, I asked you, just if you could check, well, maybe I should check because I sent him a message. Let me see if he replied real quick.
No, he's not going to have class today.
Okay, there he is. Sorry, but yeah, I didn't think he could. And I should have maybe gotten something ready for it. Let's go back to our notebook. Okay. So you notice that if you watch the lectures, he laid it out a little differently. Now here, we looked for some coefficient that would make these 2 vectors identical. But here, and we could do that by inspection, right? But here, we couldn't do that by inspection. We see this, and it's pretty obvious There's nothing we could multiply V2 by to make it equal V1. But in a pure mathematical sense, let's at least put some text on what he said. So let's just call this general check for independence. Now, I'm trusting that you guys like it when I show you how to do the LaTeX math. And I'm going to be lazy. I'm going to go up here and grab this stuff because it's really the same stuff. So we can leverage from this. But this is always available to you. In fact, Hugo, if you would please, and I'd rather do it than keep you from listening, but if you can just make sure everybody has the link to this notebook. I'm pretty sure they do.
I'll do so right away.
Okay, great. So he was showing, and we don't need all of this, so we're not talking about the norm. So I think we'll have enough. What I'll do for now is just put some distance between that and this, and in case we need some pieces down there. But we wanted to look at, when we put in a variable for C1 and C2, we really wanted to see, I'm just trying to think ahead. All we really wanted to say was some V1 and V2, there we go. Yeah. If we could find some set of vectors, excuse me, coefficients. So here I'll do C1 on V1 and C2 on V2. And here what we want to say, if there are some, I'm trying to think how to word this best for y'all. Saul does it so well. If there are if, there we go. Now I've got it. If there is a C1 not, oh, I bet there's a, let's see, I'm going to guess. I'm going to hope I'm right. Not equal, no. Let's see if it's, might have to go look it up, which it's good for y'all to see me look things up too, I suppose. I'm just trying to guess. Okay, so let's do it. I'll show you all. I'm not the perfect at staying organized, but I do my best. So I'm data science blog. I know it's blog. I know it's LaTeX. And when people see the way I work in any realm, they tell me you're so organized, and I feel like, gosh, if I'm organized, I feel sorry for other people. But I try to stay organized. So we need. I just always feel like I could do better, but I do put some energy into it. We're looking for not equal. And you know what? Let's do that a faster way. Not equal. Boy, must be because y'all are watching. Not equal. Oh, shoot. Okay, we're going to have to brute force it now because I can't find it the fast way. See, it should be. Oh, it would be over here. Delimiters. Yeah. Object and set theory, maybe. You'll yell at me if you see not equal before I do. That's all I'm looking for. I would have thought, oh, maybe down here. Oh, that's frustrating. I would have thought this would be easier to find. Maybe I looked right past it too. Hard to believe it wouldn't be up here. Well, that's logic and set theory, though. Ah, there it is. Oh, it's just in brackets. Math lab, math R lab. Ah, that's confusing me. Okay, we'll try some of those. That's maybe. Well, here, I'll just take this much. See what happens. What? I'm just really confused why you do it that way. Okay. How about we do it on a separate line so we're not in the middle of everything? I don't think we'll have to do this kind of searching very often, guys, but this is, okay, that didn't work. That's interesting. Got an idea. Don't know that this will work, but maybe it will. No. Okay, let's try pieces of that. Harlem. Oh, shoot. Maybe just more of a general search. LaTeX, math, not equal. Oh, I bet that'll do it. So back here, there we go. In E. Yay. All right. You'd think I could have figured that out without going to search for it. Okay. Oh no. What did I just do? In E. Oh, no wonder. It's outside. I need to, silly Tom. Okay, I should probably put all of this in dollar signs, the part that I'm trying not uh, zero. Now we want to close that. So it looks really ugly. If you try to do text outside. And by the way, LaTeX, it's ancient. Oh, thank you there. Y'all look in the chat if you want to link. It's a view only link, but you can make a copy of this notebook through that view only link and then have it at your own disposal. And then some, and C2, I should say, and or some C2 in E 0, or saying 0 equals C1 V1 plus C2 V2. And then we don't need this stuff. Then the vectors are dependent. Now let's look at that again. And then that's as much that This is so insanely simple that it can be confusing. And I think to make this more clear visually, we'll do it this way. Okay, let's look at this carefully. If we've got v1, v2, and they're just some vectors, if there is a c1 not equal to 0 and or some c2 not equal to 0, or 0 equals to, I should say, to satisfy the equation, etc., then the vectors are dependent. However, the counter is true if C1 and, I gotta fix that, but I will. C2 must be 0 to satisfy, and we'll figure this out here in a minute, the equation above. Then the vectors, are independent. Now let that sink in a minute while I fix this. Please think about this. This means that the only way to get the addition of the vectors to be 0 is for the coefficients in front of each vector to be 0. Then they have to be independent. It's saying that we're getting new information by adding those. Now, since we have a little extra, would y'all like to go just a little longer and see an example in 3D? Even if it's just you going, I'll keep going, or we could save it for next week. But I think really this section deserves a 3D example. What do y'all say?
I think I would love it, but I'll wait for others to see what they want in the chat.
Yeah, let you go, and I know in the chat if you'd like to do a 3D example.
Okay.
Okay, I think Aaron wants that too. Same for Chris, same for, yeah, so I think we're good.
Okay, I'm not seeing, they must be chatting with you privately, which is fine. I hope they're not afraid of me, that's all.
No. I think it's a mistake. I know Ayodeji's
Okay.
chat is the general domain. Then Chris, I think he mistakenly sent it to me privately. But,
now, one thing I would like to know, is this clear? I mean, sometimes these mathematical statements are so insanely simple that you think, no, wait, there's got to be more to it than that. But I assure you, this is meant to be just a really obvious statement. In fact, mathematicians love to boil things down to this level of just stupid, obvious elegance. And so much so that it can almost be confusing. But they really, in my experience, it's getting to that most simple understanding of what they're saying. But I'm going to just step through it one more time just to make sure. So if there is, yeah, exactly, Chris. But I want you to understand, when you get it, you'll look back and go, oh, yeah, I was overcomplicating that. That is a very typical reaction, but let's look through it still. Oh, we should be doing that. Okay, and I'll catch other. Oh, yep, another one. Okay, if there is some C1 not equal 0, and or some C2 not equal 0 to satisfy the equation 0 equals C1 V1 plus C2 V2. In other words, you are finding that V1 or V2 can be a combination, a linear representative of the other one. In other words, they're the same, they might just be different magnitude. Then the vectors are dependent. And we could have had this go out longer. In fact, well, let's do this same thing. Well, when you watch Saul's lectures, if you haven't watched it yet, this is what he's getting at, and he does it in true Saul Kahn fashion with some good 3D visualization. But here's another way to look at it with the tools we've been using. So let's do our trick that we did before, where we're doing this sort of stuff. And we're going to do it more in a NumPy way, though. So what I'll do is I'll gather this stuff that we need, and I'll go ahead and do all of this, but we're going to simplify it quite a bit now that you have that stuff. And we're gonna do this in a visual way now, what we just saw. Now we did it with the span, but we're just going to do it in a way that it looks even more obvious, hopefully. So I'll make a text block and say visualization of above principles. I think that's the right principle. There we go. And I'll paste that in there. Now we're going to simplify some things. So we've already got, excuse me, we've already got V1, but maybe we should keep it this way. It kind of reinforces what we've been doing. So the I direction is the X direction, same as the X direction. It's just I hat is the unit vector in the X direction. Same for J hat and K hat. But let's just do this much. This is the same thing we were doing. It's just broken down into components now. And we're not going to plot V3 this time. We're just looking at how V1 and V2 relate to one another. And that means, let's see, just going to also just call this the title and put stuff in there. But because of our new dark mode, we're going to just say that the color equals white. I'm pretty sure this will work because I did it somewhere else. We're not going to worry again about plotting V3. Let's see what this gets us. Okay, it is, oh yeah, I'm still trying to, oh, we just need a different title. You see, it's nice that we can put the LaTeX math in here. There's some setup you've got to do to your collab, but you usually only have to do it once. So let's just say visualizing V1 and V2. And we don't need all this other stuff. There we go. That should do it. Oh, I'm a little worried though. Well, it worked before. Let's just see what happens. Oh, very nice. Worked. Okay, so we got our pretty printing of V1 and V2 up there. But again, and I could have moved these around. Let's have them start at the same point. I was just putting them end to end here. We'll have them start at the same point. And here's the whole point. I mean, we're really belaboring the obvious, but we're learning to talk like linear algebra people. And what we're saying is, here is V1, and here is V2. And we can see that as we're looking at V1 relative to V2, we have new information. Whereas if we, let's add another text block here, and we'll just say visualizing, independence. And then, but we want to also visualize dependence. So I'll take this hard work we've done here, copy it into my keyboard buffer, and then we'll add this. Visualizing dependence. And I should be saying linear, because this is linear algebra. We're working with linear principles. Why? Because they're easy. Well, relatively speaking. And so we'll repeat that code, but we just got a little change, some little changes to make. Now V1 is going to be 1, 1. I hope I might have inverted it from the above, but I think you'll get the principles. And I only had to change that one spot. But now when we look at this, you can see that one's right on top of the other. They're starting at the same point, but really they're just along the same line. We're not getting any new information here. But if we were to, say, go into 3D, it'd be the same principle. If we had 3 vectors and one was like this and one was like this, the other one would have to come up like this out of this plane. So right now, let's look at this way. We're in 1D space. We're in a 1D space. That's all we have an information for is we could do a transformation and we'd say, well, this is just one dimensional. But here we get a little new information and it forms not a line, because this is a line, right? But this defines a plane. Well, Tom, how does it define a plane? Because when we were up here and we did a finite span check, we were looking, these are all lying in the same plane, okay? And then, but these, even though we had two-dimensional vectors, they're just lying along a line. And then finally, if we are looking at this, and we've got a plane defined by these 2 different vectors. In order to have new information and go 3D, we have to have something that rises above this plane or below it. In other words, that's how we get, when we get additional information, we've raised the dimensionality of the real numbers we're working with. So let's write that out. In fact, I'm doing control and then click, and I want to move these above that. So we talk about dependence first. And so what we're saying is, get a cough drop. 1 second, guys. Take away. When we add new information, we have, wait, I should say with new information comes with increased dimensionality comes new information. Now let's remember why we're looking at linear algebra, why we want to get good at it. Well, as we keep learning the principles, you'll see that this helps you understand linear regression super well. But it'll also help you with logistic regression, because logistic regression is built on top of linear regression. Well, what else is built on top of those two? Neural networks. And why do you want to understand neural networks? So that you can deeply understand things like deep learning and transformers. So you guys, by paying a lot of attention to what we're learning here, and then when you start to code neural networks, it helps you deeply with the principles of coding those neural networks too. So we should stop here and discuss. And as you're forming your questions, what I can do is go look at another notebook and try to just give you some nice 3D plotting tools. So please form some questions, either come up and start asking them, or ask Hugo. And what's up? You might think I'm a normal man that, when you get down to it, honestly is controlled by his wife. And that's partially true. But in reality, in my workspace, I'm controlled by my dogs. Okay, I'm gonna go hunt for some fun 3D plotting things. Let's see. There's a great 3D plotting routine for notebooks. I don't have it memorized yet, so I thought I'd go get it for y'all so you could use it. There we go. This is it. It's super simple. It's a Plotly Express. So this is interesting. We're going to have to do this next week, because I'm going to have to play around with how to fake out arrows in Plotly Express. That will take a little research on my part, or one of you can be ambitious to go do it, but at least I've put this in here. I'll just put some new stuff for arrows. Now it should be very much like Matplotlib, but I don't want to take the time this morning to do this. It'll be ready for next week. So that'll be a little work I do ahead of time. And then what I'm hoping you guys will do is watch these two videos and think about them and imagine the code you would add to your copies of this notebook that will help you understand via code better what you learned from these lectures on subspaces and the basis for a subspace. And then the week after that, we get into some truly fun stuff. Now, don't let the number of lectures fool you. These are probably longer by necessity. And these are probably anywhere from 3-minute to 5-minute videos is my guess. So this is where we'll start to have some fun, but you will be super glad we've spent careful time on these lectures when we go there. Okay. I'm eager to hear if there are any questions. Is there anything you'd like me to go back over? Now, it's okay if you're having trouble forming your questions, but please, okay, good. Okay, so Chris, I'll go to yes, okay, no questions for now. Okay, good. And then Arun's saying, can you please share the YouTube link for these classes? Well, let me show you something. That's what I've been doing here. If I click here to go to this first lecture, Khan Academy opens up, and I recommend just watching the videos right in here. So I'll just start this one to show you. Whoop, I've already watched it, so I can replay it. Now, you can go to YouTube, but I recommend just watching them in here. Because then you're staying within the system of Khan Academy. Now, it's probably something to do, I don't know why it's doing this. Usually they just play right away. It could be something to do with the fact that I'm on Zoom right now. Oh, I've had this before anyway. There we go. I don't know if y'all can hear. Yeah, you bet. Now what I'm going to do is pause Saul right now and go back over here so that I'm actually literally, if we click here, it'll open up a new tab and just go, it's the same place really, but it was going to this point. And yeah, that's what I've been adding to each one of these as we've been going along, is just putting the links right in here. And so next week's, of course, we'll have a super big, we'll just have these two, and the week after that, all of these. So I'll add all of those for you as I'm building this. I'm not trying to put pressure on y'all, but what I'm hoping is y'all are watching the lectures ahead of time. You're getting a feel for what we're doing here, and you're trying to fill out your notebook ahead of time, and you're so excited about what you came up with that you're saying, Tom, can I show what I did? I mean, that would be the best way for us to do these classes. But if it's taking you a while to get to that point where you want to work ahead and show your own work, it's okay if it takes a while. I'm just saying that would be the ideal thing to do. And let's talk about some things here. What should you all have? You should all know how to use Colab. If you don't, we have some introductory lectures on that, but you're watching me use it, so that should help. And then you should be have a Khan Academy account so you can track your own learning there. And you should all have a free GitHub account. and posting your information there. Like, it's okay. I would only ask if you guys make your copy of this notebook available to the world, put something in there that said, I learned this from Thom Ives of integrated machine learning and AI. And then, of course, you can modify it and stuff. But just say it was started from a kernel of learning from Thom Ives. That would be nice. Personal brand does mean something. Okay, Hugo, you have a question.
Not a question really, but I want to take up a challenge, and I think if anybody wants to join me, they can. So this week, I think I'm going to do I'm going to have I want to do a live coding session of this. I just want to recode this for myself because I've just been absorbing and absorbing and absorbing. And I think if I express myself a bit in my own way, it's going to come out the way I would, the way I have understood it. And then if there are any errors or whatever, then I can be corrected. But I think I want to take it up, and I don't know if anybody wants to join me. So have it like a classwork or like a homework together, and then we'll present next week before the session starts.
Let me explain the wisdom of Hugo right there. What does a toddler or a baby do when it's first learning to walk? Well, it finds some couch or chair or something like that, and it starts to try to pull itself up, right? When and it may then walk along and fall. You think, well, you might look at that baby and say, well, that was a bad effort, but nobody says that. They're applauding their effort. And I don't know why we're so afraid. It seems like there's just starting to be people encouraging one another. Embrace sucking at something new so you can start to get good at it. I mean, guys, the best way to prepare for these lectures, watch the videos and try. But the person that tries and doesn't get anywhere is so much further ahead than the person that didn't try, because they're at least pulling up and falling. But after you do that a few times and you look back through everything and you think about it, look back through, think about it, try to code, fail, try to code, fail. Eventually you're going to say, oh, I get it now. And you're going to be teaching me things. Now, I know I've been where you are. And when, a mentor says you'll be teaching me things, it's hard to imagine that. But I had this good friend who was teaching me something, not 15 years ago. And I looked at him after he gave a presentation. I said, Lynn, I'll never be able to talk about that as good as you. He said, yes, you will. In fact, you'll be doing it within 3 months. And he was right. It just took me time of embracing being new and sucky at it. And then it got better. All right. I don't mind maybe trying to show up to some of these sessions and just watching y'all. But I think it's great y'all want to get together outside of this time. I just would enjoy watching like a fly on the wall if I can come. All right, why don't we wrap it up to give people time between now and mentoring. And I hope this was helpful. Please, Hugo and I are always trying to make this better. I guess coding real time, I should have known that would be more helpful. It's a little more embarrassing for me because you see that I have to trial and error some things here and there that I don't remember or haven't come across, but that's real life. So if watching me go through that helps you, then that's what we should be doing. All right. Let's call it an end, Hugo. I guess we could stop recording. And okay. Then, but I'm going to hang around just in case there were some questions. I really do want you guys to feel free to ask more questions. I'm going to keep this sharing open in case there's a question. Now, I think it's a little harsh, but there's a Chinese proverb that goes like this.